here's an example of topic of optimization, and this is the setting. Find two positive numbers whose sum is 24 and whose product is a maximum. So let's figure out the information we got. We got two numbers. I'm going to call the two numbers x and y. So we got that x plus y must be equal to 24. And we also got that its product, it says that whose product, so that's the multiplication of both of them. So we got that x times y, we got to make sure that these two guys complying with this x plus y equal 24, and this multiplication will produce a maximum, this multiplication. Now here plays a problem because we have only solved kind of problems in where we got only variable, functions such as this one. We got something like, well, let's say we got an area in terms of x, and we got 3 times x squared minus 2 times x, well, whatever actually. The thing is, we have only solved things that has only one variable. That's for one reason that we'll figure out later on. But the thing is, this is a function, 8x times y, that is a function in terms of two variables, will be in terms of x and y, because these two guys are variables. So, but we haven't covered and we haven't get into this idea of multivariable calculus. So we got to figure out a way to find a solution which only implies one variable. Now, the thing is, I'm going to do something else now. If I suppose I got, I'm going to do this on the right. Suppose I got, well, okay, I'm going to pick values for x and y. Let's say I got pick values for, let's make something not so smart. Let's say we say, well, I got 1 and 12. So 1 times 12, that will produce a 12, of course. Now, let's suppose I pick another set of values. Let's say I make 2 times and 12. I will make 2 times 12, which will be 24. Suppose I make 10 and 14. I will make, of course, 10 times 14. That will make a 140. And let's pick, I'm just going to pick another value. Let's make it 3 and 21 will be 3 times 21. That will make a 63. Well, I just picked random values for x and y to produce these scenarios. But the thing is, just we are requested to solve this out with one condition. We are requested, of course, to find two positive numbers, but the sum of those two numbers must be 24. So technically, if we do not consider this sum has to be 24, we could have infinite number of solutions. And that is why we got to use this thing that in math, we call this beauty to be a restriction. So I'm going to name it, it's a restriction. I'm going to actually better write it with more space, because this is something very important. You will find this a lot in many these kind of problems of optimization. This is a restriction. And the thing is, if we consider this restriction, well, for instance, we should decline using this as a valid answer, because 2 plus 12 are not exactly 24. And we can as well decline the first guy for the very same reason. Will be 1 plus 12 will be equal to, this is different from 24. And these two guys, they are actually, if you add up the 10 and the 14, you will get 24. And if you add the 3 and the 21, you will get 24. But we have to make sure to be to fall in as well, to comply with this condition. So the way we do that is that we took this restriction and we involve the restriction on the equation that we are trying to optimize, or to find the best possible answer, because that's the idea of optimization. We are not requested to find any answer, but these two are answers, but we are not requested to find just any answer. We are requested to find the best possible answer. So we got to introduce this restriction into this other area. So I'm going to include the restriction into the my objective. Call this my objective, or the function that we are going to optimize. So what I'm going to do, I'm going to pick this expression, will be the x plus y equal to 24, and in other words, I'm going to solve for one of the two variables. So let's say I'm going to solve for x, and let's say for y, 24 minus x, and now with this guy solved, I'm going to substitute on the same expression that we got before. This guy will be a of x times y. A of y will be equal to x times y. But if I substitute this y within this expression, something funny would happen, because we got x times the y, which is 24 minus x. So now the thing is, once we substitute the y, I'm going to actually frame it. And actually going to use the same colors, I think would be nicer. This y would be the 24 minus x. Well, actually, once we have done this, something funny happened, because this expression, this function is no longer in terms of x and y, because we took away the y from it. So this will now be a of x. There it is. Now, how about if we try to figure out the best possible answer, or the maximum possible value that this function could take, where we know how to do that? The thing is, this is what actually we have been doing, but I'm just going to make something else. I'm going to multiply this x times these two guys, just because I think it'll be simpler to take the derivative of it. So these two guys, instead of using the product rule, I'm just going to take the derivative out of these guys. So this would be a prime. The derivative of a would be derivative of 24. That would be 24 times x. That would be 24. There will be minus derivative of x squared. That will be 2 times x. Now, in order to find the critical point, or the candidate to be a maxima, we will equalize this expression to 0. From here, I think it's a piece of cake, I will say. We are familiar with this. The x equal to 24 over 2. That will make a 12. Let's say 12. And now, from here we got to figure out, again, we got the testing. Well, of course, this will have to be a maxima, because otherwise it would be kind of pointless. This is an example to be solved, but I'm still going to do it. So this would be the x equal to 12. I'm going to pick values after and before the x equal to 12. I'm going to pick, let's say, a of 0, even though this is not a realistic measurement, or because this has to be a positive numbers, and 0 is, well, actually you would consider it positive, though it's okay. So let's say that will be 24 minus 2 times 0, and at the end we'll got this to be 24 positive. So this is positive. This is telling us that the function is ascending. Now I'm going to pick another one. Pick a prime of 20. A prime of 20 will make, of course, a 24 minus 2 times 20. Now this 2 times 20 will make a 40. So this would be a negative 16. Now this is a negative 16. Of course, what this is telling us is the function is descending because of the negative sign. Descending. Okay, so this is ascending, and then it's descending. So, well, of course, this is a maxima. It has to be, otherwise the point would be kind of pointless to find this problem. This would be a maximum now. So what we are requested to find, we are not, just be careful, what we are requested to find. We are requested to find the two positive numbers. So we already found one. One of them, it's uh, the two numbers, the two numbers. We got one, which is x equal to 12. Now, what is the other number? So the other number, we got here the formula, green. Here is the formula to find y. Now, in this case, it would be, something like 24 minus 12. We just substitute the x on the formula. I'm actually going to write the formula. So we substitute the 24 minus 12 because, x would be 12. So this will produce at the end that y is as well 12. So these two numbers, in a sense, x equal to 12 and y equal to 12, these two guys, write it. So what is telling us that x equal to 12, I would say that these two numbers at 24 and their product is a maximum. There it is. So this is actually the answer. We are not requested to find the product, so we are requested to find the two numbers, so that's it. I hope you will find this useful because we're going to use this idea of the restriction and including the restriction within the function that we want to optimize. And then after you figure out this, the restriction, you include it, and then you got the new objective, which would be the simplified and substituted version of it. Then after it, from here on, it's pretty much the same thing as all the previous cases.